Morning.
Hello.
Morning.
Good morning.
I'm eating myself since I've been wandering around and making coffee and things.
Good morning, everybody.
Morning.
Hi, Alan.
Hi, Keisha. Hi, Kevin. Hi, John. Hi, Raymond. Sorry, I'm a bit late, a little bit running behind this morning. Okay, let me capture everybody. Okay, give it a couple more minutes. Hi, Pratik. Welcome to the group. Is this your first time?
Hey, hi. Yeah, this is like first time I'm joining. I'm
Okay.
aware of OCP, but like this specific subgroup I joined.
Okay, welcome aboard. Very good. We'll do a little intro in a moment. Pratik.
Hey, sorry, like I missed the last part. Like I think there was a noise.
Sorry, I'll ask you to introduce yourself in a moment once we get started. If that's okay. What company are you with, Pratik? Oh, we've lost him. Oh. Okay, let's get started. Okay, well, good morning, everybody. Welcome to our OCP HPC subproject regular meeting. I sent out a quick intro yesterday into what I wanted to discuss. Basically, I've been sort of noodling really over. I've been away a couple of times on vacation, and then we had another presentation last week, last meeting. So it's been a while since we gathered together. But we were we were looking at the various progression of NVIDIA with their latest architectures and where they sort of pre-announced they're going with their Vera Rubin architecture. And you know, I think we had a meeting on that, and I was discussing that maybe we should look at where we are with the HPCM and whether we should take a relook at that. And so, as I think about it, if we look at where the puck is going, I think there are some bigger changes going on, and you know, some of the shifts that we were looking more at into the future seem to be a little bit more imminent. And so I thought it was worth to take a step back and really discuss what were the changes that we're seeing, and I guess the likely directions that we're going to see from the big guys, and also whether we should rethink what we're doing in terms of our ideas on ground up architecture ideas. So really, it's just an open brainstorming session today, and I wanted to prepare a little bit more slides, but I've just got some bullet points to share. So if I switch over to that, basically all I was going to talk about was the high level trends. And I think there are a few more that I did think of some others, so we can capture them. And if anybody's got any others, I'll be happy to sort of. In fact, I won't go in presentation mode. I'll put it here, and then we can actually discuss each one of these. So, in fact, what I want to put there is really racks going to 1 megawatt. And 800 volt, right? Okay, so yeah, these are in no particular order, just as they came to mind. We're sort of seeing this potential where we're going to get this backside power delivery seems to be coming. I see, and I guess there's a question is to how quickly is that coming? And in that sense, you know, are we going to start seeing these devices needing backside power. I think that means, I think that presents a lot of interesting complications and maybe even opportunities. So I wanted to put that down as a point. It looks like Olivier's just dropped, sadly, because he may have been able to make a comment from Intel's perspective. We can also see that NVIDIA at least are introducing I/O chiplets into their package now. So just on the Rubin architecture, these little die at the edges are actually I/O die, which I think is a sort of an interesting addition that I was sort of half expecting. And my view there is when you start to introduce separate I/O die in that package, they're likely going to be subsuming the NIC functionality. So we'll lose NIC cards. Like if you look at the Blackwell architecture at the moment, they still have NIC cards, but I think that's just going to be subsumed in the package with everything else. So the entire computer effectively is literally being absorbed into a single package. It's really except for the extended media where you want to go to serious amounts of memory beyond what HBM can deliver. So the I/O chiplets and this chipletization trend is obviously, we've got HBM has been the staple of a chiplet attachment, and now we've got these I/O chiplets. There's lots going on in various work groups in OCP and elsewhere in terms of chipletization. If you look at what AMD have done with their MY300 series, they've got quite an elaborate 3D chiplet architecture that's really well thought out in terms of being able to swap GPUs with CPUs and even potentially FPGAs, etc. So anyway, but a specific point here is we're seeing these I/O chiplets being introduced specifically by NVIDIA. Then the other thing is we're seeing these rack powers. If you've been involved in the OCP Open Systems for AI sort of strategic initiative discussions, then you will have heard that really everyone's looking at 1 megawatt racks, an individual rack that is consuming 1 megawatt. And it looks like it needs a power supply rack right next door to it. But bottom line is they're talking about bringing 800 volts DC straight into the rack, actually. And I'm not sure whether that's going to be right in terms of how that maps into the infrastructure, but certainly high voltage, and they're bringing that right to the individual rack. And potentially, I've even heard discussions of 800 volts down to point of load power supplies, in sort of reducing the number of stages between the step downs. In order to minimize losses, and also the introduction of the 800 volts as close to the compute as possible is to minimize the IR losses and the huge amounts of copper you need to deliver that power. And finally, not finally, the optical transition seems to be happening now. We are seeing the switches start to introduce the co-packaged optics. We're seeing, I think we've all sort of taken a look at Avicenna with their hundreds of LED solution. And I still think that's quite interesting. They seem to be making a little bit more progress. I think they got investment from NVIDIA and a few others. And they announced a partnership with TSMC, where TSMC were going to manufacture their optical receivers. And so it looks like they're probably, fingers crossed, going to be coming out with some product. And I think that might give us bandwidth increases, even for like direct interconnects. I sort of am wondering whether we can get a very efficient, like instead of electrical I/O, we just go to optical I/O built on the backside of these devices. And so you could have something like a vertical, if you imagine in our HPCM architecture, we're plugging the media in at the back of the processor with interconnect. We've got PCI Gen 5 and going forward 6 and 7, etc., with like 8 or 16 lanes, giving us a limited amount of bandwidth, but potentially we can get to terabytes per second to one of these, between one of these pieces of media, with an optical connector that could be a lot simpler and a lot less challenging than the
I think you run into a problem with the fiber connections, and that you see people gluing fiber onto things, but then they do it inside a plug. So you've got fiber going to silicon inside a plug, and then the plug plugs into something else, which is copper, and you hit a bandwidth limit there.
Yeah, well, so with the Avicenna, they build the LEDs into the layers on top of the silicon itself. So the LEDs are there.
But it's going to fiber becomes a problem. It's
Yeah,
like
yeah.
they're trying to glue bundles of fiber onto things, and I've been looking at the free space optics stuff for a while. So why that was the thing I was saying a long time ago with this group, is like, don't go through the edge connector, just go face to face in free space.
Right. So, when you plug these modules in, there would be no fiber. Basically, all you'd have is you do face to face, just like you said. So therefore, you wouldn't. But even though the media and the compute were really quite close together, and so therefore copper could reach. If you use optical, you just get the bandwidth density benefit. Even with these low-speed optics, these LED arrays, because they're so dense, these arrays, in 1 millimeter, you can get like 400 of them.
Yeah.
But
it does require a particular format of hardware where you can plug in boards, and you
would need to design new interconnect
well, it's more of a lack of interconnect, and then there's the issue which we're tackling in the OCP.
It's a mechanical alignment as opposed to interconnect.
Yeah,
So optical, for the free space jump, like you said.
But if you were at the optical fiber conference earlier this year, there were guys doing stuff where they were doing 3D printed optical things, where you could build a block of material which would guide your photons around for you.
Right.
It's quite interesting.
Interesting. Well, yeah. So I mean, maybe that we're still a bit researchy there, and maybe not. Obviously we know that NVIDIA managed to stay in copper at 200 gig. Everyone's talking about 400 gig.
Well, you just run into the problem that it gets harder and harder, and the pitch of copper is not great.
Right, exactly. Yeah, that's my point. Effectively, that's my point. Yeah. And I think the other stark issue is we are pretty much stuck at 5 picojoules per bit or thereabouts for any even half decent distance these days. And if you go to silicon photonics, they're still in the 5 picojoule per bit, albeit they can go much longer distances. But in terms of your bandwidth to power out of a particular device to 5 picojoule per bit, we'd like to get HBM bandwidths off chip, but we can't get there because of the 5 picojoules per bit.
Well, it's a question of so this is one of the things we're looking at in the Open Atomic Ethernet work stream, is that if you're looking at power, it's the total power, not necessarily what the cost in transferring a bit is, because if you can do the bit faster, then your processor's not stalled, so you save power. So you kind of need to look at the whole equation rather than one little piece. And This is a problem forever in high performance computing. There's people doing networking and there's people doing compute. They're not.
Yeah, it's a game of whack-a-mole is a crude answer to a crude agreement with what you're saying. But 5 picojoules per bit. If you look at the moment, HBM is knocking the door of, I don't know, 8 terabytes per second with 8 of them in a package or whatever it is, a terabyte per second per one, going higher. And if you said, well, I want to take that bandwidth off package, I remember when I did my FMS presentation back in 2022 on this, I think I worked out that 5 terabytes per second of off-chip bandwidth would be 700 watts at like 5
Well,
picojoules.
yeah, the thing is, don't go off chip. Like
But well, obviously,
within
but
the stack,
you can't make a, well, that's where wait. So actually, that's a good thing because I haven't put that bullet in here. Let me just put. I forgot to put that on there. Wafer scale.
But I find HBM is in itself an anti-pattern. I mean, the idea of putting all your data in a block like that. I mean, basically, what HBM is doing is saying we can only go so far with a parallel bus. So at the end of that distance, we're going to start stacking the stuff up on top of it itself.
Right.
And it's just a horrible way to do computing. But if you sell memory chips and people want to buy that, that's what you make, and that's kind of where we are. I mean,
Yeah.
I'm currently working with people that want to do CXL, but that's because somebody wants to buy CXL. It's not because CXL is a particularly good idea.
Right. Right. Yeah. Well, yeah, and to your point there of just make your chip bigger. I mean, that's where we're going towards wafer scale, where they're stitching the wafer. You've got Cerebras, or you've got people stitching known good wafers back into a artificial wafer. So, in fact, and on that, they're even going towards square wafers are being talked about. I don't know how real that is. Giving you better yield or better density.
Well, we got other people trying to do like reversible computing and stuff. It's a lot of it's R&D stage, and I don't think you'll get there unless people put a lot of AI into the EDA.
Well, and that's my point. I'm trying to say what are the things that are less researchy and more actually seem like they're about to happen. And why this list here is what I believe is what is you're either seeing happen. It's not still in, or well, it still might be in research in terms of really polishing it off.
You want to add diamond substrates in there, or transparent substrates. There's people are doing diamond wafers, which are good for getting the heat out.
In production or in research?
In production, there's a company in San Francisco, the Diamond Foundry, selling diamond wafers.
Okay. I mean, I'm not sure what that does to us. I don't think that makes any difference.
Yeah, I mean, the thing is, if you do a two-dimensional computer, which is basically a mesh of an array of processors talking to their nearest neighbors, but in a flat surface, if you can stack those and use optical communication, you can do it in something like diamond wafers, and then you build yourself a 3D computer where you can actually model things like 3D spaces efficiently.
Right. Okay. So
you might take a while to get there, but you can kind of do the free space optic stuff on regular hardware at the moment.
Oh, actually, that's a good thing. Actually, on glass substrates,
glass doesn't conduct heat well, but diamond does.
Okay. All right. So glass substrates. I guess diamond wafers are not going up to the size of glass substrates.
No, I think they're at 10 centimeters, but I think it's a kind of slow vapor deposition process to use.
Right.
I think people are using it for power electronics applications.
Right. Okay.
You can do things like drop a layer of diamond on top of something, and it's not conductive, but it distributes heat for you, so you lose hot spots, which makes the stuff last longer.
Right. And then the last one, which I've already mentioned, is wafer scale compute, where including these square wafers, where you get more devices on a wafer. It looks like that seems to be we're again, if you just look at what NVIDIA's doing, their Rubin Ultras, they're now stitching 2 of the Rubins together, and so in theory, we're going to see this long line. Assuming they double it again on the next one, but you can see them going all the way to putting these on a wafer. And if you look at, I mean, Jensen's been showing this.
You just don't get the yield if you try and do that kind of thing.
Yeah, but they take known good die and they stitch them back into a wafer, and then they do redistribution layers on that
Yeah.
stitched wafer. So I think again I have no idea on yield in that sense, but that's better than a Cerebras approach where you just etch the entire wafer.
Yeah. Cerebras are a bit insane.
Right. So and there's the optical stuff that's going on. So yeah, and I guess that's the. I'm just going back to my other presentation. So when you think about all of this, in my mind, it's a case of if you're going to skate to where the puck is going, there's quite a few significant changes to bear in mind. Now, the HPCM module. In fact, I should have opened up a presentation in the HPCM module. Let's just see if I got one in my recents to hand. Let me just flash up this one. Yeah, this is my sort of general deck. So I've always presented this slide, right? So you know, what I'm saying, you've got your compute, you've got your memory, and then you've got your fabric, your high bandwidth fabric. And I've always been of the view that your processor, and then if we look at that, how that translates to our module, it looks physically like our module. We've got the high performance processor and we've got the media plugged in vertically. And you potentially, you know, you can either plug media in or you can plug I/O straight into the high performance processor, or you could, if your media had 2 ports of I/O, you could plug the fabric into the media for a fabric, a shareable port, whereas the local port is then dedicated to a low latency, ultra low power going to the processor. So this is something that I've been the backbone of what I've presented before. And in my mind, this is still, and what you have here, by the way, is the I/O on the processor is only one type of I/O, and it's a memory interface type I/O. And you turn it into, because everything that a software engineer does is he writes to an array and somehow it magically squirts out an Ethernet port or whatever, or a NVLink port, etc. And the idea is that those I/O pieces would be buried in this. Instead of having a NIC card is just pretty much damn useless. It just converts 2 I/O standards from one I/O standards PCI to another one, Ethernet, InfiniBand.
I think that one's changing. I mean we're
Right. Well, exactly. And so if we
Yeah.
if we go to more of a, this layer needs to be redefined, and I think all processors should have the same array of I/O being a load store memory interface, and then customers can pick and choose heterogeneous processors from multiple vendors that all have the same I/O, a bit like we all use DDR memory, and we can build our heterogeneous compute.
Stuff you can rewire that quite quickly, so you don't need fixed sort of I/O stuff for that. And then we're discussing smart NICs and FPGA stuff, so we can change protocols and things.
Yeah, well, but in my mind, we need smart memory. Smart NICs are useless. The smart NICs are just shifting compute to where the NICs are.
They are very smart. Some of them. Some of them have a fair amount of compute on them and specialization.
Right,
so,
right.
So the
Exactly. But if you had the vertically, I mean, this could ultimately take you to your desire, Kevin, which is you don't need the big processors. You just need an army of ants of little processors with a ton of memory stacked on top of them. But I think there's a balance there of sometimes you need a big ass processor, but you would also have this army of amps processors with with memory with 2 ports. So you basically merge the smart NIC and the memory stacks together in the H.
I think the parlance we have in other groups is XPUs. Where you know you have processors that are in a big mesh, where different processors are doing different things for you.
Right.
So I mean, my view of the HPC thing is that we should be doing things where you can try different chips together in the HPC environment and see what works,
Right, exactly.
and then
Exactly.
pull them and rewire them in a chiplet system, because you can make a chiplet system in a matter of days, probably, if you're
Right,
not making the ASICs,
right.
but you're not going to
And
get.
I think a chiplet should have that one interface being a memory interface between everything.
Well, the thing is, you can get things which are general purpose chips that have all these interfaces like the FPGAs, and then you say, okay, I know what it does now, and I can build myself that with like some other form of that chip core. I mean, the thing I'm dealing with at the moment is a big Altera, FPGA with a whole lot of hard macros on it. But its sort of power efficiency is like, a fifth of doing an ASIC. So,
Right, well, obviously, yeah, or worse even.
yeah. But it's there as a prototyping thing. I mean, I see the HPC thing as something where we can work out what the workload does, do stuff with FPGAs and a honky big processor, and then say, okay, now we know what it does. We can use specialized XPUs and get the power down by a factor of 10.
Right. Well, yeah. So the idea is this is a heterogeneous. You can put any XPU in this layer, and it will be compatible with this new smart memory, which includes the local port. They all have 2 ports that are like a NIC, and they have some compute in that logic layer that provides near memory compute to the vertical stack. And custom HBM is potentially taking us in that direction, and hopefully Elian are successful in getting their IO approach. So Elian are sort of behind this approach. That, in fact, I talked to them when they very first started about these ideas, and that's the direction they've taken. So, so as I said, this basically turned into our module. Our module. So you've got the compute at the bottom with the media stacked up in the E3 format. So this was where we've been. But in my mind, when in fact, if I let me just snapshot this a minute. If I just grab this little block. Paste it in here. So here I'm sort of thinking that we that what we're going to get to here is good. We've got this. Now we've got 800-volt power layer, so that's going to be coming in. So this is our source here, and then we're going to have some. Oh, and by the way, the other thing I completely missed out is I think that we could be shifting from direct liquid cooling with lots of pipes and manifolds to immersion, which just seems so much simpler. Now, with that said, that's an easy statement to make, but there's a lot of challenges with immersion as well.
There is a thing with photonics and other sort of communication that you can spread stuff out without losing much. And then we have performance. So the more you spread that out, the less of a problem your cooling is.
Right. So
the tendency to we're packing more and more into the box, but then the box gets harder and harder to cool if you do that. So
yeah.
It's not necessarily the best direction to go in.
And now I've got power. It's maybe some level of intermediate power conversion. And then you've got and this is all going to be in a sort of like an immersion fluid where this will be cooling the processor directly, and then you'd have and maybe this becomes one layer actually, but you'd literally have the point of load PSUs directly mating to the surface of the silicon, and assuming that some sort of copper, then the power supply could also act as a heat sink into the immersion fluid, is what I was wondering. And obviously, if we've got this power architecture, so it's sort of, in my mind, and this is really dangerous stuff, right? I mean, 800 volts is ASHRAE. You kill people instantly with this. So they're talking about the only way they can make this work is to make this a robot-only data center. But I'm wondering if you could design the infrastructure where, again, in our wall of compute thinking, that basically this sort of infrastructure here could be built in somehow in the immersion chamber before it's filled with liquid, and then this is just lives in the immersion chamber, and you then immerse these things into this. So anyway, this is just an early thinking of mine. But so it's still our modular approach still holds true, but suddenly things get a little bit more complicated. And any of you that have looked at Tesla Dojo from a few years back, they actually did a wafer scale where they rebuilt it to the wafer scale, and then they did have the power supply stacked on top like this, bringing it in. Although it wasn't backside power, they did bring the power in vertically. The other thing here as well is that we will be going to wafer scale. So basically that means one of our modules wouldn't be big enough. Suddenly you start to get to, if you're talking 300 millimeters, then a module would be 300 millimeters in size. So that takes, and then is that really just a step and repeat of our module idea on a wafer? But obviously it's all homogeneously one big unit instead of these multiple modules. So that complicates things. But then again, this is the I/O side of the house. And so I just feel that this stack is still very relevant of if you've got your power in, flowing through the device, flowing through the media, and to the I/O, stitching everything together. And that stitching everything together can get extremely complex. But if this I/O layer here became just optical, and you could attach, okay, all the fiber attach challenges, you're absolutely right, Kevin. But they've done like these fiber, these optical companies have actually done where they lay fibers, really thin fibers in like a real flat surface, and they somehow seal them in gel. So it's like a PCB with a ton of fibers around for it. If you've got them going everywhere in different directions for some sort of all-to-all interconnect between a massive array. And so I guess there's that could be inside the immersion chamber, and then the optics just comes out the top and goes elsewhere. Or is it serviceable? The other thing is, would you want these media bays to be serviceable? Like pluggable, like we've said, are they less power dense, that they could be like some level of conduction cooling down into the fluid if you had some conductive path between these pluggable modules? But again, they would be cooled by the immersion fluid a little bit more indirectly, so therefore you wouldn't have such a good thermal transfer compared to the kilowatt plus processor.
Alan,
Yeah.
I sent you an email about John Schaff from Berkeley Labs,
Yes.
Lawrence. They have been thinking about same issues you are discussing here, so we might as well also listen to what they have. It can benefit us when we design.
Yeah, so happy to do that. I thought John Schaff and his team were heavily working with the open chiplet economy group, and they've I didn't know. They're doing some interesting stuff, and I've presented to them. But so unless they're doing something else that you're on about, it seems to be more chiplet oriented.
Yes, they are interested in chiplet. Yes.
So and you can find out all that. John Shaft's, obviously they're presenting all that on the chiplet work group. So I know everything they're doing if it is chiplet related, and I'm not sure they're not looking at the system architecture level. Like this is the big mechanical pieces. They're looking at how do you package a couple of chiplets together in a package. And I've talked to them about the interface layers here. So, I mean, yeah, we could get them to present here, but I think most people here that would be interested in that already attend the chiplet work group. So I think it'd be a duplication. That's all, Haitian.
Okay. So he attend a new Friday 8 o'clock meeting sometime.
Right. Yes.
So
And his group is they've got their what they call their system work group, but their
yeah,
system is inside the package really. And they're talking to us about some of the software as well.
yeah,
So
and they are also interested in power management and how to reduce energy consumption and things like this.
is that in the silicon or is that at the again, I think that's all in the silicon, right? And in the chiplets themselves.
Yes, you're right.
Right. Yeah. Yeah.
Both actually, because when I talked to him, he said he works with people who are looking at the whole network, like a data center, how to save power, but also they are looking at the chiplets and interconnection.
Right. Right. Yeah, I guess there's overlaps. I mean, I don't mind anybody coming to present if it's relevant. I mean, the players here. I think the power companies, the 800 volt. The other thing to look at is a lot of my learnings here, certainly on this power side, are from going to the Open Systems for AI strategic project. Now and there's presentations going on there about 800 volt power plus and minus 400 volts, the challenges of that, but how they're going to integrate that. So these things are going on in all of the OCP work groups. We've all got to sort of I make it a point of myself to make sure I'm involved in them all, so I know what we can pull into this group. But there's you can go to the Open Systems for AI and watch the videos. There was a complete workshop for about 4 or 5 hours on you can find everything about the 800 volt powers ideas. So yeah, I mean, I don't really necessarily want to. It's in essence, I think our group is saying, with everything that's going on in the different disciplines, how do we pull this together into a system package, into a system architecture package, looking to where it could go. I mean, at the end of the day, you've got NVIDIA's telling us where they're going, so you can just do like we did with OEM and just say, well, NVIDIA has done it this way, so we'll copy it. I don't know. AMD and Intel are, while they are heavy players in the open systems for AI, they're all behind closed doors in their own teams, deciding how they're going to do their own NVLink 72 or jump beyond it. And they want OCP involved, but only when they've got something that's done and dusted, and then they'll contribute it to OCP. So we don't really see what they're thinking, that we could get ahead of the game or we could align with them. I mean, look, so in all seriousness, though, guys, I mean, there's this from a need perspective. I should have updated you as well. From a need perspective, there's the AI silicon startups that are trying to compete with these guys, and obviously you can't plug one of the AI startups chips into an NVIDIA system. I mean, NVIDIA have sort of semi-opened up their architecture to let people play in their infrastructure, which is so that's a possibility for people. but you're still sort of sealed into the NVIDIA ecosystem. Or the AI silicon startups have only got the make a PCI card or make an OEM module. That's their only real choices today. And arguably the OEM module is, rear view mirror by several years now. And so how are those AI silicon startups going to compete with NVIDIA if they're working on architectures that are 5 years old? And so it's a case of how do we get something going in the open that all of everyone else can actually contribute and compete. And so I was working with Untever on that, but sadly Untever ran out of money and their engineers were just absorbed into AMD. So we don't have that vehicle anymore of where I was actively working with people on a simplified version of our HPCM to go into the DCMHS architecture. So to bring there, because if you follow DCMHS, which is the modular hardware servers, they were just like regular servers with PCI cards, and it's like, how could you introduce something similar to the HPCM as an accelerator into the PCI to give you more bisection bandwidth, better cooling, etc. And so we were working down that path as a more of a pragmatic step towards HPCM. I think that could still be viable, and I am talking to other startups as we speak in terms of where there may be some interest in following that up. But the HPCM itself, going all the way, I think we probably want to look at in my mind, I've got some ideas where it'll still be HPCM type based, but we might need to make some fundamental changes. Things do pan out. I think the thermal management is very interesting. I think the immersion cooling is if that direction really is going to happen, is the next big step. Then trying to work out how you fit into that ecosystem much better. Is
you can always try going for something different, like low latency computing. Like how do you arrange hardware so you get minimum path distances between things?
Right. Well, I guess that's what they're doing by packing all these chips into a package and then needing.
I mean, the wire lengths can be quite long.
But in the physical world, the system architecture, which is our bailiwick, your biggest latency challenges are distance. But at the silicon level, that's obviously down to the silicon guys. So, and at the end of the day, the other thing is I'm coming up to a 5-year run here on driving this. If people think, we had a good attempt, we came up with some nice concepts, but we just couldn't get anyone interested, and so time to hang my hat up and let somebody else take the reins. If any of you know of people that are saying, when's Alan going to get out of the way and we can do a better job of the HPC sub project, then I'm happy to talk to people and see how we transition that over as well. But I am working with AI silicon startups and other heterogeneous processor startups, and I think they need a vehicle where they can have a chance of competing with the big guys, and I don't think they've got one right now. They've got only let me demonstrate my silicon in a PCI card or an OEM module, and then see where they go from there. But they end up not having a competitive solution at scale. So either they've got to tackle different markets, like maybe edge applications where you only need a couple of devices, or you don't need a complete NVL72 type architecture. But anyway, so I still think the need is there. I really think that the big boys own this, obviously, and it's becoming more and more closed, and we're all about open. And so I'm just.
I think one of the problems I've had with this for a while is like you're still stuck with one edge connector. things.
Well, exactly. I mean, that's my. That's
I think, I mean, if you came up with an approach which had used more edges in the faces of your boards, um, you might get somewhere people have not managed to get before.
right. Well,
I mean, we're trying to essentially we're using two edges when we're like
to be honest, that's what we were
stuck in the
doing
back.
here. I mean, this I/O straight into the back of the chip was giving you far more pluggable
Mhm.
capability. I mean, that was the idea. I was hoping that would capture people's attention, but it didn't, right?
Well, I mean, again, you've got like they've got the board that things are plugging into there, but then there's the other end of the board. Once you've plugged your boards in, you could do something where
Yeah, no,
you're
absolutely.
getting
Well,
both ends.
again, that's exactly right. I mean, the idea here was this is the local interface, and we'd have a fabric, a data plane, so optical I/O coming out this side. That was my idea. And originally electrical here, ultra low power, 1 to 2 picojoules per bit to the processor, and here was straight to optical, ideally,
Well,
a gig.
you could do copper on both ends.
Well, then you got all the freaking copper problems of this is for going distance. So, I think you want to get to optical at a picojoule per bit. You want to be no more than a picojoule per bit, if not less. It is sort of stage one
Mhm.
on both sides of this, and then you've got your media in. And I think this module's probably too big. I think we'll end up with an HBM with flash stacked on top. And so probably these modules might actually just be a lot smaller, like a quarter of the size or whatever, but they could carry still terabytes of media or many terabytes of media. So
Yeah.
anyway, yeah, that's really any more. I mean, I've in my presentation here, I've just tried to capture the key shift in sands, and yeah, I have some ideas, but knowing what we went through with HPCM, they're probably going to be too radical. And also, I think this wafer scale, this gradual shift towards making the package bigger and bigger to keep, everything millimeters apart and the energy moving stuff between the different chiplets as low as possible. It looks like that trend it looks like TSMC are really
I
honing
think
their
you'll
scale.
get wafer scale
Yeah.
substrates, I think, but you're doing wafer scale like Cerberus do it doesn't seem like a good idea to me.
No, that's right. No, and if you look at what TSMC is doing, it looks like they're taking known good die off of a wafer and then rebuilding it back into a wafer and then doing redistribution layers of copper between those known good die. It seems like that is becoming a pretty like a standard practice at TSMC. I'm pretty sure we're gonna and again, if you just got he's been giving us hints for a long time. He's drawing wafers of the entire back while I'm NVLink 72. He's
Yeah.
done this for a reason. These are the actual real die, and he's saying, look how small this is, and we need a 19-inch rack for it, right?
It's a horrible design, the whole thing.
Well, right. No, I know. But it's what is working and what people are paying billions and trillions of dollars for. So
Yeah.
you've got to live with it. So and how many people are buying
Well,
those?
I mean, it's just suboptimal in many directions. My
Right.
feeling.
No, agreed.
Yeah.
But it's pretty.
There is, however, always the need for like packing as much as you can in the box, which is like more what this is about than the
Yeah.
actual
So
compute.
here he's saying. I mean, then we need this wafer, which is huge, obviously. We need 140 kilowatts to burn inside there, right? So how would you call 140 kilowatts in a wafer? But Jensen is just putting the real wafers side by side and showing. He walked in with it was a big wafer, albeit, but he walked it in and he said, "This is the real size of all the chips that make up NVLink 72 rack scale machines, 140 kilowatt machine." So it's you can see he's probably making variants of this as we speak.
Well, it's incremental engineering. It's like, it's not hard to tell where they're going most of the time.
Right,
So it's
exactly.
never far from where they were last, you know.
Yeah, no, exactly. That's it. And so you know, when it comes to that system level, I mean, obviously, the more we go into, if you get wafer scale with this sort of solution, then I guess, you know, it's becoming more and more. It's a billionaires club. If you're, you know, if you're not a $1 billion company or even a $1 trillion company it's getting to, you can't play in our industry anymore. You know, you can. I mean,
Well,
the way
they kind of engineer it that way. You know,
yeah, well, yeah,
it's like the guys who do the tools for your chips. I mean, they make shitloads of money, but they don't do a very good job on it. You know.
right.
Yeah,
Well,
but
and
the
I
fact that
guess Jensen's play to this is he's opened up his NVLink interfaces if you want to, and so you can put your own custom AI chip in here instead of his, or your custom CPU in there instead of Grace,
yeah.
etc. So he is opening up to that extent, but obviously he owns the infrastructure pie, which is a very clever.
Yeah, well, I mean, a bit of what they do own is CUDA, and people are doing a lot of the AI stuff with CUDA, and that's where something like Untether becomes unstuck. Unless you have the software stack,
Yeah,
you
no,
can't do better hardware.
it is an interesting challenge. So yeah, actually, with his opening up of these, I mean, that is quite an interesting. I mean, for AI silicon startups, maybe this is one of these only paths, you know.
Well, I think I mean a lot of the guys are not doing this. They're out on the sort of inference side on the edge, doing low power stuff, which is probably a lot more interesting. And
Yeah,
you know,
I
that'll
think
come back in.
inference at the extreme edge and ultra low power for inference at the edge. There's I think there's plenty of opportunity for innovation there for sure. But this big machine market, yeah, it's gonna be interesting. It's yeah. So anyway, so that's really where I'm at. I'm like any of you guys and pass the word around. I mean, just let me know if there's other ideas. Let me know if I mean it would be really good if it'd be great if AMD would just say we're prepared to talk about what we're doing in the open to really get everybody going.
Well, the R&D group I'm in Samsung at the moment is sort of looking at FPGA upload and compute stuff.
Right.
Interested in doing their own supercomputing.
Well, yeah, the memory guys own a lot of this business, right? But and they're in a great position to, if they could get their heads around doing the compute, they're in a brilliant position to.
I mean, it's generally herding cats, and like you know, Samsung, like other companies, they make their own processor for phones, and those are efficient processors. So people have, to some extent, people have to get their heads around the fact that, you know, just because it doesn't do 5 GHz doesn't mean it doesn't do compute well. You know, it's all about power efficiency.
I mean, the trouble with Samsung is they got fantastic research. They do some really fantastic research, but if they can't see a $100 billion market out of it, they kill it or they just fail to ramp it.
I mean, no, I mean, I've been there before, and like they do keep going at these things. Same with Microsoft. You know, they will keep making attempts at the same thing and failing until they get what they want. If they've got the budget, they've got the budget for it.
I keep my fingers crossed for them. But them and Micron, you know, and Hynix. I mean, I think in terms of them becoming a big player, it's in this world because the memory is so central to everything now. They do have the opportunity.
Yeah, but I mean, the computer architecture sucks though. Like unless you change the computer architecture and some of the tools, you're going to be stuck here for a while.
Yeah.
But then you're looking at what the AI itself does and how you can, you know, you can change how you do things quite quickly with AI in the software world.
Yeah.
So that changes the game quite a lot. And you know, one of the things is actually trying to work out at OCP. One of the things I'm trying to do is say, okay, like what's your workload doing, and what's the best machine for that workload?
Yeah.
And the HPC piece is more about, okay, how do we find out what the workload does? And you kind of need the HPC machine to work out what the workload does. And then having having done that, you can then say, okay, now we can build a specific chiplet machine for that and save ourselves, 80% of the power, and
Yeah.
then we can worry about ASICs. But
I'm just noticing we're at the top of the hour. I thought Pratik, I thought you dropped. Sorry about that. And Josh Guest. Hi, Josh. Have you been on before? Oh yes, you have. You're Extreme Networks. I got you. So maybe Pratik, would you like to just do a quick intro and then we'll close the meeting? Is to yourself, who you work for, and your interests.
Yeah, sure. Hey, sorry for that. Like at that time, some technical glitch. So I'm aware of OCP, and I'm joining this high performance computing subgroup specifically. So recently I joined a company which is we work in semiconductor in the manufacturing or it's manufacturing part, but we do a lot of HPC stuff. So like uh, when the wafers get produced, right, after that we do the verification of those things. So we need compute, like we work on a lot of computes, and so it's not like a very large cluster form, so but packed, and we have high speed interconnects and so mainly around that, so we are looking for new generation of the product, and for that. So I'm looking for something if we have some reference architecture, so mainly to get that info, or just coordinate or discuss some.
Okay, well, thanks, Pratik. Unfortunately, you're a little bit muffled there. I think your audio connection is a little bit. I got most of that, but would you mind just popping your company name into the chat, please, and then I'll just log you here as well.
Yeah.
Apart from that, we're at the top of the hour, so thanks, guys. Good discussion, and we'll see where we go next. Okay, thanks very much.
cheers. Bye.
Excellent.